Yeah,
So I'll quickly share my screen. All right. So the
sure.
session is this one, end-to-end deep learning. I'll try to keep it as quick as possible. This is a lightning talk. Will only be cover like 15 minutes. So this is no way in going to be covering all of the aspects of end-to-end distributed deep learning, but this is going to give you some key points where you want to, if you want to work on an end-to-end application in a production environment. How can we use distributed computations or distributed systems for machine learning? So without further ado, let's just start. And before that, I just want to extend my gratitude towards TFUG India Summit. All the OC members are doing really well, especially during this time. So I'm really glad that we still are having these sessions, even though we are not able to do it in person. A bit about myself. My name is Akshay Bahadur. I'm a senior data scientist as Lowe's. I am currently working in the search and recommendation team, where we mostly do customer related customizations. I'm also a word developer expert in machine learning. All right. So before we start, an important link. So if you want to follow along with the session, probably check it out after this session. I have added this link. So just go to bit.ly/TFUG 20, and you'll be transported to my GitHub, which contains all the slides, links, and everything, all the resources that is going to be necessary for this particular session. All right, so we'll be talking about Apache Spark, just the basic aspects and why exactly Apache Spark is such a is quite popular when it comes to distributed computation. So Apache Spark in itself is not very well suited for deep learning, but it is very well suited for distributed computations, and here's the reason why. Of course, these all features are very important. So one of them is it's quite fast. So one of the reasons why Spark became really popular is because it was pretty quick. And if you want to read about the history of Spark, this actually came from the MapReduce project that was taken up by Google. But Spark kind of covers all the other aspects that were missing in MapReduce. One of the things that was very important for making Spark very popular is the powerful caching mechanism that was used, because earlier people had to write to disk even if they were working on if they were working on distributed systems. Let's say 10 of these nodes are working in parallel, all of them had to write intermediate data on the disk and then read from the disk again. So with Spark, we had the concept of caching in the RAM or even on the disk as well, and this made Spark very powerful because it became quite fast when it comes to distributed computations. And at the same time, it's highly scalable, so you can scale out onto different nodes. It's fault tolerant. So all these features made Spark a very good choice for people who had huge amounts of data. And then around, I think, last 5 to 6 years, people started wondering if we can use Apache Spark for machine learning or not. So machine learning on Apache. So this slide is only about machine learning, not deep learning. So machine learning on Apache Spark is slightly different from what we have seen previously, maybe in from TensorFlow, Keras, or PyTorch. So Spark machine learning on Spark is based on the concept of pipelines, and this the concept is very important because in distributed systems, whenever we have to develop the consumption and production of data, we consider the usage of pipelines, and therefore Spark also uses the concept of pipelines, where each pipeline does the whole work of transformation up until prediction. So we have a concept like data frames. The data frames is similar to a data set. So we will just use that analogy going forward. A transformer is an ML model. So basically, transformers transforms the data. So a data frame or a data set with features can be transformed into a data set with predictions. Okay. And then we have a concept of estimators. Estimators are nothing but learning algorithms. So basically, whenever you run, whenever you call the fit function in Keras or in TensorFlow, that is equivalent to an estimator in Spark. So all these three concepts are very important because this is directly an analogy between Apache Spark and other popular frameworks in machine learning like TensorFlow and Keras. So we'll use this analogy going forward and making sense at later stage. All right, so we have Spark ML pipelines. Let's quickly look at how exactly will a Spark ML pipeline will look like. So we'll have the data. It's pretty commonplace in the form of a data set or data frame in Apache Spark. Then we'll do some pre-processing. This pre-processing could be, regularization. No, sorry, not. This could be normalization, or you want to do some feature extraction. So this pre-processing can be a part of a separate estimator. An estimator, as you had seen earlier, is kind of a transformation where we make some changes to the internal data set, and we present another data frame at the end of this estimator. And then finally, we have another estimator, which is our actual learning model. And then this whole system forms a pipeline for Spark. And then finally, we make predictions from this. So this concept is important. We'll go ahead and try to memorize on try to understand this concept and use it when you're talking about distributed machine learning or distributed deep learning. Okay, so just a quick deep learning refresher for everyone. So we have data and labels that's coming in. We have some pre-processing. Pre-processing could be it could be any pre-processing a technique, either it's normalization or just feature extraction or scaling. And then of course we have some layers, and layers, of course, we will have these gradients, and then we have to back propagate and adjust our weights according to the gradients. And then finally we'll make these predictions. So this was just a refresher for how deep learning works. And now we try to connect these dots that we have just seen. So now we come to distributed deep learning. Okay, so distributed deep learning in itself has a lot of features. We'll be only covering one of them in detail. But other than that, if you want to have a look at all the six, we have, I think, six features, we can have a separate discussion offline. So distributed deep learning is very useful for parallel experiments. If you want to run parallel experiments and you don't want to use the same sort of node, then of course you can do that. Hyperparameter optimization is something that I've used quite a lot for distributed deep learning, and it's very effective because you can train parallelly with different hyperparameters and choose the best one. Um, and then, of course, we have other things which are also distributed training, and that is something that I would want to discuss today because this is one of the key aspects which made the distributed deep learning quite popular. The concept of distributed deep learning. Okay, so we'll talk about distributed training in detail. So, of course, when we talk about distributed systems, you have to think about the concept of parallelism. And in distributed training, we also have different parallelism techniques. First is model parallelism, which means that within different GPUs, you can uh, specify different layers. So let's say if you have 6 layers, you can have GPU 0 can have the first 2 layers, and then going ahead, different GPUs will have different layers. And this technique is not very popular because it kind of does not make a lot of sense, to be honest to me. Then therefore there came a second technique, which is data parallelism, which means that each GPU will has the whole definition of the model or of all the layers, and then we will distribute the data among them equally, or depending on some some sort of algorithm, and then based on that we will perform our training. Now what you'll realize in this case is that how all the GPUs are in sync, and this is something that was the main question and was the main challenge when it comes to distributed training. One of the advantages that, let's say, if you use only one GPU, our error over a period of time, decreased something like this. It was quite linear, but if we added more GPUs, our error started going a lot down. And then, of course, with more and more GPUs, the error became down, but at the same time, it became more complex. So I'm going to assume that we will not look at the complexity at this point because that's not really our point of concern. We just want to make sure that we just want to touch upon the concept of distributed training and how exactly is it used and how can you use it going forward. All right. So as I already explained that synchronization was of main concern. So if you can see that there's a technique which is called as parameter server, where we had a single service, which is the parameter server service, and it got the delta weights or change in the weights after every training epoch or every training iteration. And then based on that, it used to get the weights from all the different GPUs, and it's going to compute that and going to return the weighted average or just the average of all the weights to each GPU. So this is pretty commonplace, and it makes a lot of sense as well because we have a central service which runs and it does a lot. It does most of the work for us, and it gives back the important. At the end of each epoch, it gives back the information that is required. All right. So now this technique, of course, had a lot of pros and cons as well. So the pros were, of course, it's fault tolerant because even if one of the GPUs went down, we still get the weights from other GPUs, and we can similarly perform our gradient descent going forward. It's a both asynchronous SGD. So SGD is the concept of stochastic gradient descent. Asynchronous means that some of the workers could be slow. Some of the GPUs could be slow, but at the same time, it will not block other workers. And the cons were that usability was tight coupling. We had a single point of failure. So if the parameter server was down, then our machine learning or a deep learning model would not train. So this was a major bummer for us. Scalability, of course, was an issue. We can add more GPUs because distributed machine or distributed systems has the concept of scalability, but because we have one service, which is the most important aspect of our whole system, scalability becomes an issue. And convergence is a problem because you have if some of the workers are slow, it's going to be a bit tricky to because let's say what if the worker is back online and then you have to give the weight to that worker as well. So it had a lot of problems as well as it has its pros. Then there was a technique called as all reduce, which was I think introduced by TensorFlow itself. It has been heavily used by TensorFlow and as well as other open source frameworks. So what it does is that it uses an all reduce strategy. So this is different from parameter server. So let's say if we had 4 GPUs and let's say we are considering 2 GPUs at this point. So GPU 0 will not talk to the parameter server. It will talk to GPU 1 and it's going to send it to wait. Okay. Now what's going to happen is that this GPU will talk to the next GPU and then similarly it forms a cycle. So we are not dependent on a single service or a single parameter server. We are internally, exchanging weights and calculating the weighted average of these weights for the next epoch. So this became quite popular and it solved a lot of problems for us. So now we'll talk about machine learning in production. So when we are talking about machine learning in production, we talk about 3 phases. Getting the data is an important concept. We'll talk about how we train the models, and then we have to talk about how we deploy these models in production. And we'll have to talk about 2 use cases. First is the real time, where you are getting the data at runtime. You're not training it, of course, because you're getting it at runtime, and you're making predictions at runtime itself. And then we'll also talk about batch predictions. So basically, let's say over a period of time, let's say over a period of 2 or 3 days, you want to get the information, and then you want to train the model at the end of let's say 2 days or retrain your model. How will you do that? So with the concept of distributed machine learning or distributed deep learning, this became quite easy. And uh, so we'll see. So in real time, we'll talk about messaging queues, which was I think already covered before. So we'll use a very popular messaging queue called as Kafka. So it gets the data in real time, and then it has a streaming engine. So streaming engine will probably just get the data and clean it a bit, and then we have a real time feature store. So it's going to get the features from that incoming data. Of course, we are not training it, so the training step is blank. And then finally, we have some prediction service in real time. And there is a trained model which comes from somewhere. We're not sure about that right now. We don't care. There's a trained model which gets the data or gets the data from Kafka at runtime and it gives predictions to the client service. So this is the architecture for a real-time service running in production. Now, we want to also train the model or retrain the model again and again. So we have a concept of data lakes, which contains petabytes of data, and then it contains historical data. And then based on that, we use Spark ETL processes, basically these pre-processing, extraction of the data. And then we have these feature stores and label stores. And then based on that, we have batch training, which we could do on a Spark cluster, on a cluster. And then we have a model store. Based on that, we collect the best model, and that trained model is then used in the real-time processing. And then we also have a batch prediction service. So let's say if you want to perform some calculations on batch data set, let's say batch means probably batch of 1 day, 2 day, 30 minutes, 60 minutes, and then make prediction. So this is how a cycle will look like for a production machine learning environment. All right. So and going one step ahead, which is still a very novel concept, is just I wanted to give you a thought of it. So let's say how exactly. So what we have seen is that Apache Spark is pretty useful for data processing. And we've also seen that Apache Spark is works very well on CPUs. Okay, but deep learning, because it has a lot of matrix multiplications, the most optimized way to do it is on GPUs. So can we do one thing? Can we have these nodes with CPUs and GPUs, so we can perform the pre-processing on the CPU, and then when we have to train the model, we can use then GPUs on the same nodes. And this is one of the concepts that is still quite new. So we have something called as Hive, which kind of you can think of as the data lake itself. And then we have some ETL tasks. ETL tasks are nothing but uh, we just saw feature engineering and pre-processing steps, which are doing done on CPUs. Then we store the information on HDFS, and these are just features which are written to Hadoop file system. And then based on that, the training is done on GPU itself. So we are combining the power of CPU plus GPU to make an end-to-end machine learning or a deep learning pipeline. So this concept is very important. And then of course, post-processing can also be done on CPU, which is like model serving and all. So this process or this whole pipeline is quite interesting, because now we can utilize both the CPUs and GPUs going forward in production, and we will be saving a lot of resources. At the same time, we are kind of modernizing our whole production environment. So with this, I would like to end the session. I have two links as well. So if you want to check that out, there's a collab link and there's a Databricks link as well, which is mostly just the code for this. So I'll just quickly go through one of the sessions. I think I've already opened it. So there's something called as Apache, sorry, Uber Horoward, which is used for distributed deep learning on different GPUs. So right now, if you see, it gets this number of GPUs from it. So I will not go into the details of it because this is going to be slightly a bit more time consuming. But at the same time, you can see that most of the things that you have seen are simple training or simple Keras or TensorFlow configurations that you have already seen before. The only thing that changes is that we use a different optimizer. So other than that, we use a simple error delta optimizer. Right now we are using same Keras optimizer, but we are optimizing it based on the GPU number of GPUs. And then of course we can also have a distributed optimizer strategy, which is of course comes out of the box from Horoward itself. And then at callback, we are using a broadcast global variables callback. So basically, uh, it makes distributed training quite easy for everyone. I mean, for the whole system. And then at the same time, it's just making some predictions and calling the fit method. So you can have a look at that. And of course, it does not make a lot of sense on a Colab notebook because Colab only gives you one GPU. But if you have like a cluster that's running parallel computations, in that case, Horoward comes into picture and is quite popular. At the same time, if you go to the Databricks link, you will see that there's also something called as deep learning pipelines, where you can use Apache Spark quite effectively with TensorFlow retraining tutorial. So this is basically a tutorial on transfer learning. So I'll not go into details of it, but feel free to check these out. So these other links of them are in the if you just click on this, you will transport it to this page of Databricks. You can just look at this, have a look at all the code snippets that I have created, and feel free to ask me any questions. In the interest of time, I'll not go into the details of it. So if you have any questions, I'll be more than happy to answer them. In the interest of time, we can also take it offline. And if you have any feedbacks, reach out to me on akshaybahadu.com and let me know your thoughts on the session. And there are a couple of references that I took. So if you want to, have some references when you go back, you can have a look at these two links. And then, so this was it from my side. This is akshaybahadu.com. You can find me on Twitter at akshaybahadu3. And the link to the slides are bit.ly/TFUG-20. So with that, I'll just like to wrap the session up. And I think Ali, if you I'll be more than happy to give you control.
Sure. Thank you so much, Akshay, for that awesome session. It's always awesome. Okay. I hope there are multiple questions, but with the scarcity of time, we would not be able to take all of them. But let's take the one. Okay. So
Yep.
Can you please pop one question the back and team? Also, till then, if you want to join the chat afterwards, you can maybe
Sure.
answer them in the chat, or else it
Yeah,
is
yeah,
Twitter. You can follow him on
yeah,
Twitter and LinkedIn, and
yeah.
that will be awesome as well. Okay, so let me pick one question. Um,
Sure.
so there was one question from Dipanjan saying that brief on how the backdrop might work across workers in an epoch.
Okay, so Dipanjan, of course, is like the one of the best guys that I know in machine learning. I'm really happy that he asked this question. So it depends, of course, on the particular framework that you are using. So in case of so there are different frameworks. So right now we have talked about Apache. We have talked about Horoword, or which is Uber's open source framework. We can also talk about Big Deal, which is Intel's framework. So all of these have their own white papers, which you can have a look at if you want to get into the details of it. But backpropagation, how it works is that because the data is parallelly, you have some. Let's say if you have 10, 15 rows. Let's say if you have 10 rows and you have 5 different nodes. So two of the data points can be given to one node, and then going forward, five of these nodes will have two data points, and then of course they can perform this learning on these two data points, and then based on that it's going to after this epoch has ended, let's say if it runs for one epoch, after the epoch ends, it's going to give the information back either to the parameter server, or it could also do it amongst themselves. Like one node can send their updated weights to the other one, and then similarly after that, there are different strategies on how the weights are updated. So either it could be an average, weighted average, or there are other complex techniques as well. And then once you, after one epoch, once you have the updated weights from all the five nodes, then the second step is performed. So this is one of the basic major concepts. And if you understand this concept, I think it makes very easy for you to deep dive into distributed training.
Thank you so much for that answer. So yeah, you can find Akshay on chat or on Twitter. And with that, I would like to thank Akshay for his time.
Yep. Thank you so much. Appreciate it. Yep. Take care.
Okay. With that, we come to our second, the last session, and we also have a project showcase afterwards. So